Hello everybody, I would like to give some highlights about method comparison, and in the specific case to talk about robustness, and I will take in account the brand new Bayesian Deming regression which can be made robust, Frequentist method which are not very popular but available, M and MM Deming, and of course the Passing Bablok family. And part of this work is on GitHub, especially for M and MM Deming. You will find a package which is MCR which is a package which is the MCR package with added functionalities, and then I have made available on CRAN Arstan BDP, which is for Bayesian Deming regression, and for the rest we will use just MCR functions to assess the robustness of the Passing Bablok family. And part of the work has been already published in 2021, and the brand new stuff about Bayesian Deming is available on my GitHub homepage. Here is just a script, an R script on my RStudio, and I'm going to load MCR which actually if you don't want to use M and MM Deming, you just can substitute with plain MCR, which is exactly the same, but I load my own library to perform also these two regressions. And then of course we need Bayesian methods, and here we go. The idea is to use this script to generate synthetic data, and this is the script I used in 2021 publication, so it's nothing really special. I set also seed just to make it easier to reproduce, and this is actually the data set. I call it that, and it's better, it's handier to order it, so I just make order and renumbering, and as you can see, this is the data set which will be used to test the regression methods. Okay, first step is just to calculate some reference on this data before modifying the very last points and introduce handcrafted outliers. So this is simply the pure data, and we can run Deming in analytical form. We can run equivariant Passing Bablok also in analytical form. We can run Deming with bootstrap and BCA confidence intervals. Coefficients of these two will be the same, confidence interval not necessary. And we have also the traditional original algorithm for non-parametric Passing Bablok of 1983, which is on the list. So I can execute all these four methods, and on the other side I can use Bayesian Deming, which is available since 1 month on CRAN. This is version just non-robust, just normal, and this one is with a slightly, or actually not slightly, it's a moderate robust with a 5 degree of freedom for the residuals. So we can perform this too. It takes a little longer than Frequentist approach, but it's quite fast. Okay, and we can just watch the plots. I grouped them in group of 4. So, and the first 4 are Deming analytical, Deming bootstrapped, and the two non-parametric Passing Bablok procedures. Wait a second, excuse me. Yeah, right. And you see the slopes are just almost perfect 1. Actually, it's not really 1, it's 0.998, and this is better visible watching the coefficients instead of these plots. And just to compare, I have done a similar plot keeping as reference Deming analytical and equivariant Passing Bablok, and then watching what the Bayesian method delivers. And this is the two lower here, the Bayesian, and this is Frequentist. And Deming and non-robust Deming, they provide exactly almost the same result, and we have also similar results between Passing Bablok and this moderate robust, you see, degree of freedom 5 Bayesian method. And watching coefficients, well, they are all pretty much the same, and this is 0.998 for Deming analytical. Of course, it's exactly the same, or should be the same for, yes, they are the same for the bootstrapped confidence interval. Of course, the confidence interval are slightly different. And then for equivariant or traditional non-parametric methods, we have a slightly lower level, but actually it's the same. Basically, it's the same. And if you watch Bayesian confidence intervals, you see we have exactly the same. So there is no surprise at all. And now this is just a reference. What is interesting is coming right now. So right now what I'm going to do is to introduce 10 outliers, and I'm gonna do it in a leveraged fashion. So I will just pick the 10 highest values here and drag them down by 30 units to have just a leveraged outlier and see what happens with all the methods in presence of the worst case scenario, which is the presence of a massive amount of leveraged outliers. So to do that, first I do a copy of the data, and I just keep the very first 90 data separated, so I can double check another time just with only those datas. And here is the step where I just drag down the y by 30 units. Okay, so now if I plot the data, you see that those red data have been moved down by 30 units, and we have this group of leveraged outliers. And the idea is now to see what happens with our regression methods, and what about robustness of those methods. So let's go. We have Deming analytical, equivariant Deming, original Deming, equivariant Passing Bablok, original Passing Bablok, and then we have the whole row of Bayesian Deming, starting from the non-robust one, and then you see going down to the most robust one, which is Bayesian Deming with Cauchy distributed residuals, which is degree of freedom 1 on the t distribution of the residuals, and we perform them. The first three are rather quick, and then of course these are a little bit slower, so I just click and wait. For those I just make standard 4 chains and 2000 sampling iteration, so it takes a short while. Okay, and now let's just take a glance with the plots, and I take in the upper part just a reference, So in this case, Deming and equivariant Passing Bablok, and on the bottom part of the picture we have Bayesian methods, and as you see, this is Deming frequentist approach. The value is 0.87, so these points are dragging down the slope. The exact same phenomena is seen on non-robust Bayesian Deming. The extent is slightly less, but actually it's almost the same. And this is equivariant Passing Bablok. And interestingly, you see that there is a drift on the slope. Anyway, it's not a big drift, but it's about 3% of drift, and this means that non-parametric methods are not so immune to the massive presence of outliers. Actually, it makes sense because in Passing Bablok methods, the way the slope is assessed is just to make all possible pairwise slopes and then to take the median. So if you have enough outliers, in this case we have 10% of outliers, then the median will be shifted, and of course it's not that robust. It's robust, but it's not completely robust, and many people do not realize that, but it's like that. And on the bottom part, we have, in this bottom right, we have 9 degrees of freedom for Bayesian method, and you see already with this rather weakly robustness parameter, because degree of freedom 9 is not that much robust, we have already 0.95, which is not good, but it's quite surprisingly good, because this is not really robust. But now if we just keep this as reference and we check down with more robust Bayesian approaches, we just see that with 6 degrees of freedom we already get the same result as Passing Bablok, and 6 degrees of freedom is just not really a very strong robust method. Gelman and company, they just suggest to use degree of freedom 5 for most robustness in general for Bayesian methods, and if we take 5 degrees of freedoms, we have already more robustness than Passing Bablok method. And we can of course go lower, and you see we are further and further, 3, 2 and 1. We go narrower to the ideal line. We don't really get to the 998 level. We go down to 990 or something like this. But anyway, all these levels of robustness are way higher than the non-parametric procedure. And actually it's also interesting to check quickly the 90 original data, so just check those data without the outliers, what they would provide. And of course we can do it with Frequentist method and also with non-robust Bayesian method. And we just take a look at the coefficients, and as you can see, actually the 998 level, which was the original data, is confirmed. So those data were not didn't depend on the last 10 data to provide the correct slope. So this is just simply a proof. But now what is really interesting is to go back and watch exactly the confidence intervals and the null hypothesis. And when we just check, this is for Deming analytical, this is just non-robust method, you see we got 0.87. that was in this picture here, this level, and you see the null hypothesis is rejected for slope. It's no surprise. This is a wrong rejection because those are outliers, and exactly the same happens for the non-robust Bayesian method. Okay, but then the surprise comes with Passing Bablok, because with Passing Bablok you might think that you get a non-rejection, but this is not true. With Passing Bablok you also get a rejection of the null hypothesis, a wrong rejection of the null hypothesis, because we know that those are outliers. And actually this is the same with original algorithm and also with the equivariant algorithm. You get also the same, you just get a rejection, just because there is a drift on the slope, and all this median that have been shifted because of this 10% of outliers leads to this wrong result. Actually wrong, yeah, that's wrong. Now things gets interesting, because we can do the same on the Bayesian method, and with a 9 degree of freedom, so a weak robustified, we have already seen is 0.95 the slope, and just we get rejected, so it's not enough robust to make a correct analysis. But once we move to more ideal values for robustness, the slope get better. In this case it's always a little bit drifted, but as you can see the confidence interval is wider. So what is interesting is that in this case the null hypothesis do not get rejected for degree of freedom 6, and actually in the window of the confidence interval is 0.069. I hope it's correct, because every time I run this script it's slightly different, the result, which is wider than what you get with Passing Bablok non-parametric methods. And even running at 5 degree of freedom we got pretty much the same. The slope is getting better, and actually the confidence interval is slightly narrower, but it's still larger than the non-parametric way, because it was on the average about 0.059 instead of 0.051. And actually to go down to 0.051 I have to move down further. With 4 degree of freedom we have a better value and still a wider confidence interval window, and with 3 degree of freedom we get in this case quite the same confidence interval window, but of course the slope is much better. So all those models starting from degree of freedom 6 down to 3, they are all non-rejecting the null hypothesis, which is the correct answer to the problem. And interestingly, if we go down to the most robust one, to degree of freedom 2, we still get non-rejected and quite a precise value. And with the Cauchy distributed error term, so with degree of freedom 1, we get finally a confidence interval window which is definitely narrower than what we would get with a non-parametric method. But in this case too, it's the slope is estimated in such a way that actually the model is non-rejected. So it's starting from degree of freedom 6 down to degree of freedom 1. we have the correct answer for the null hypothesis. And I have to state these two methods are probably a little bit too much optimistic, or let's say not enough conservative, but even in that case the result is correct. And actually it's also interesting to compare those methods with another family of methods, which are the Frequentist M Deming. This is quite an old method, which is now back available on MCR Pyoda, but it was a method from the 60s, 70s, 80s, which has been dropped because of this sphericity question, which is actually, in my opinion, is more a theoretical problem than a real problem, because you can run those methods with Bootstrap and then you can forget about the exact determination of the degree of freedom, the theoretical degree of freedom, and you just watch what happens at Bootstrap level. And the same can be said with this Deming, which is actually I should change this and put the which is an evolution of this method with a redescending b-square weighting mechanism. It's always like just applied on Deming, and those both are available on this package. You can install it by your own from my GitHub, and the important part is just to make the iteration a bit longer, because convergence is not so fast by these methods, and sometimes they hangs and you have to repeat it, but in this case was not the case. This is also for MM true, but I think when the data set is enough large, in this case we have 100 sample, usually convergence of this iteration method is not a problem. The problem starts when it's lower than 50 sample. And we just take a look at the coefficients of those regressions, and you see that with M Deming we get pretty much the same as what we got with the non-parametric methods, like for example this one. We get almost the same, and with MM method, actually this is quite astonishing. We get 0.996, and this is clearly an indication that our outliers have been completely ignored by the method. And to see that, it's very easy, because with M methods we have weighting factors, and we can observe the weighting factor. We have introduced 10 outliers, so I will plot the last 12 weights. So the first two are just normal, and then the last 10 could be what we see. And if we take for M Deming, you see that the weights are pretty much normal for the first data, and the last 10 datas have been reduced, but they have not been nullified. So there is a slight roll of those points into the slope, and that's why we get 0.973. But if we use a b-square weighting mechanism with MM Deming, you see that the last 10 points are just zeroed. So those points with MM Deming are completely ignored in an automatic way, and this leads to this value, which is not exactly 998, but anyway, this is very near to what we know. I have also to say that this method have been quite extensively tested in 2021, and the two methods are, well, M Deming is quite good. MM Deming is also good, but the problem is that there is a power loss, and probably it will come out that the Cauchy distributed Bayesian method could be a better alternative than this one. But anyway, this is a matter of taste. Take-home messages. I'd say the very first take-home message is do not trust completely non-parametric methods, because if you have enough and leveraged outliers, there will be a drift, especially on the slope, and then of course the intercept is calculated from the slope, so you cannot expect just a perfect result just because you are using a non-parametric method. It's not the case. If there is a rather large but not so large quantity of leveraged outliers, or just general outliers, probably the non-parametric method will somehow feel that this presence and give a slightly different result from other more robust method. Bayesian Deming is just behaving very well, and we have to say as take-home message that if we use this level of robustness, so the residuals are just modeled with a t-distribution with 6 or 5 degree of freedom, you get just the same result, pretty much the same result as conventional non-parametric method, with the side effect that probably the confidence interval are wider, and so there is a bigger chance to get anyway a validation of your method or a non-rejection of the null hypothesis. If you run down lower than 5 degree of freedom, it's still a good option, and in some cases it can be just the ideal to go down to 1. There is a risk of being not enough conservative in the confidence interval, but we are investigating on this topic, and I have to say, yes, probably DF1 is indeed too much optimistic, but probably already DF equal to 2 is a very robust alternative that could be a good choice in many cases. But if possible, I would stick on with this level, because this is quite safe, and it's even more conservative than non-parametric method, and actually it's more robust. About frequentist methods, M Deming, well, it's already known since several years, and I have tested it extensively 3 years ago. You see that again, because this is not new, it's very similar to non-parametric Passing Bablok. It gives quite similar results, and also the power is almost the same, and this has already been published in 2021. And actually what also comes out is that M Deming with the redescending algorithm for the weighting is a kind of super robust method, and can be somehow compared to degree of freedom 1 with Cauchy distributed error term on the Bayesian Deming regression. They are really something special that can be used in special cases, and we have to be aware of how we are using those confidence intervals, but they are still very interesting method. And that's it for today. I hope you enjoyed this video, and I hope nobody will blame on my terrible English accent. I'm not native, and I lean to have some very strange Nordic accent. Thank you for listening.